on direct and inverse variation. So as I said, this is a very easy section. It is not as hard as that last section, section 9.3. That's okay. We're going to do it in a little bit. All right, so direct variation is a relationship between two variables, x and y, that can be written in the form y equals k times x. Okay, k is just a number. It's specific to that certain problem. It's called the constant of proportionality or the constant of variation. Okay, so maybe k is 5 for this problem. We don't know, but it's the same throughout the problem. Okay, and there are lots of things that are directly related in real life. You can think of distance equals rate times time. So the further you travel, the more time it takes you, right? So if one value goes up, the other value goes up. If one value goes down, the other value goes down, Caroline. So, you know, maybe like our humidity is very high. Well, that means that we might have a high precipitation the next day, right? Does this make sense? So if one goes up, the next goes up. If one goes down, the other one goes down. So I have the doctor scale. I'm sure you've seen this scale when you go into the doctor's office, correct? They always ask you, I mean, you could be going in for just like your flu shot, and they'd be like, okay, tell us how much that you are in pain. And you're like, I came in for my flu shot. I'm in 0 pain. But then they also ask you when you're giving birth, which is always interesting because I'm like, I'm going to slit your throat. So that's how I feel about that. It's like, you know, 2000. That's where the pain is. But, you know, 0 to 10, this little crying person, maybe that. So I have a story about direct and inverse variation, story time with Mrs. Cox. Is when I was teaching at IU, me and the other mathies, we would all get together and we would play cards like every single night or games or whatever. And we were sitting around playing games, and a friend of mine goes and looks in a friend's fridge, and she, the girl who made this, is an amazing baker, and it was a giant tub, like a big Tupperware thing, big mixing bowl, I guess, actually, of cookie dough. And he was like, can I eat some of this? And she's like, okay. And so he starts to eat it, and as we all know, men do stupid things. Often. Sorry, guys. True story. And he decides that he wants to eat the entire cookie dough. So he's like, can I eat all of it? And she's like, you're going to be really sick, but go for it. I mean, this bowl is like seriously like huge. So he does. He eats the whole thing. And so the next day he calls all of us, and I'm the only one that's stupid enough to answer my phone. I should have known better. And he goes, you got to teach my class for me. And I'm like, it's because you ate the cookie dough, isn't it? He's like, I feel so sick. Please go teach my class. And it's an 8 a.m. class. So I get up super early. I get on the little bus at IU. I trek to his class and teach his class, and I'm so mad because I am not a morning person. I like to sleep in. I'm here at 8:15 exactly every single day. Are you a morning? I am. I'm so nice. Thank you, Faisal. Aww. That's my mentee right there. All right. So anyway. So I teach this class for him, and of course it's on direct and inverse variation. So when I told the class the story, we had a lot of fun talking about direct and inverse relations. So a direct relation would be the more cookie dough he eats, the higher he is on the pain scale, right? This pain scale. The more cookie dough he eats, the worse he feels, like the more sick he feels, I guess. So that would be direct variation. But then inverse variation, it got really gross. We won't go there. But maybe like the more cookie dough he eats, the less he has in his stomach the next day because he was really sick. He was throwing at me and some other stuff. So the less he has in his stomach and so on. Does this make sense? So inverse is where one value goes up, the other one goes down. Right? Direct is if one value goes up, the other one goes up. Okay? So we have direct and inverse variation. So this first example, it says write an equation that expresses the statement C, the cost of a dozen donuts, the cost C of a dozen donuts varies directly. Whenever it says varies directly, you need like y equals kx. That's the price P of one donut. So the cost C varies directly as the price P of one donut. C equals K times P. Now in this case, I actually gave you I gave you K. I told you that it was a dozen donuts. The price of one donut, let's say each donut's $1, then the price of all of them would be $12, right? So it's C equals 12 times P. Okay, but sometimes I don't give you what that constant is, and you have to find it. So it says, suppose M varies directly as Z, and M is equal to 120 when Z is equal to 15. I don't know why I didn't, this is lowercase c. So K ends up being 8. Okay, once you have that constant of proportionality, the K, you always plug it back into the equation. So my new equation is M equals 8 times Z. Okay, that's called my direct variation equation. So if I ask for that on your homework, that's what I'm saying. Write the direct variation equation. Okay, and then some of these questions are two-parters. So maybe you find the k and you plug it back in, but then you have to find something else that has to do with it. So this next example is like that. It's kind of morbid, this example. I mean, I like the use of the direct variation, but it's kind of like the terminal velocity of a parachutist is directly proportional to the square root of his weight. So basically it's saying the heavier you are, the faster you go when you land with parachute, which I think is kind of strange. But I mean, it makes sense, but it's a little weird. So the terminal velocity is directly proportional to the square root of his weight, so square root of W. So V equals K times the square root of W. So it says a 170-pound parachutist has a terminal velocity of 9.2 miles per hour. Okay, this allows us to find what K is. Okay, so I'm going to do the square root of 170. So I have like 13.038. And I'm going to divide, so I have 9.2 divided by that answer. And I make sure I keep that answer in my calculator. I want to be as precise as possible. So are you guys getting good at using the answer key on your calculator? So it's second negative. So when I do that, I get K equals 0.7056. So I'm keeping that in my calculator. And there's a two-parter. So it says, well, what is the terminal velocity of someone that weighs 250 pounds? So we plug in the 0.7056, and now we have the square root of W, which is the square root of 250 to find the velocity. So I keep that 0.7056077,897. I keep that number in my calculator. And I do times the square root of 250. So I get V equals 11.157. I think I said round to nearest tenth. It's 11.2 miles per hour. So not much faster. It's not bad. All right, so the question is, what do these direct variation graphs look like? If I'm going to graph it, what would it look like? As one value gets bigger, the other value gets bigger. As one value gets smaller, the other value gets smaller. So let's see. So y varies directly as x. Y equals k times x. And y is equal to 27 when x is equal to 6. So I divide it over. I have 27 over 6 equals k. I divide by 3 on the top and bottom. So I get 9 over 2, or 4.5 if you want. And I plug it back in to get that direct variation function. So my function is y equals 9 over 2 times x. Well, what shape is that? Yeah, it's a line. Right? There's no x squared. There's nothing on the denominator, right? It's a line. Okay, so it's a line with y-intercept of 0. And the slope is 9 over 2, so we go up 1, 2, 3, 4, 5, 6, 7, 8, 9 over 2. And then I draw my line in. Okay. So a direct variation function is always going to look like line, and you'll have a couple things that you have to graph in your homework that are just lines. Okay. But then we also have the inverse variation function. And the inverse variation function is the one that I was talking about, where if one value goes up, the other value goes down. Okay, if one value goes down, the other value goes up. So an inverse variation function, it says, is a relationship between two variables, x and y, that can be written in the form y equals k over x. Okay. So for this equation, we would say y varies inversely as x. So whenever you see inversely, it puts the x value on the denominator. So here's an example of one. It says, write an equation that expresses the statement Sam's speed r is inversely proportional to the time t. So r is equal to k over t. So in cross country, we always run 3.1 miles every single time. Sam was our fastest runner. You guys know that, Sam. Okay, and let's say that he runs really, really fast that time. So his rate is increased. Well, that means that the time it takes him to finish is smaller. Does that make sense? So that's why they're inversely related. The faster you go, the less time it takes to get there. The slower you go, the more time it takes. Okay, that's an inverse relation. So here's another one. So it says y varies inversely as x, so y equals k over x. And y is 4 when x is 5. So we can get k pretty easily. 20 is equal to k. And we plug it in, y is equal to 20 over x, and we graph that function. Is this one a line?
No.
Why is it not a line?
It's like that parabola.
Kind of, not quite a parabola. It's a hyperbola, yeah. It's not like the hyperbola equations we saw before with the conic sections, but it is a type of hyperbola where there's asymptotes. Okay, a rational function. Okay, what's the vertical asymptote? What can you not have in the denominator? Right, if I set my denominator equal to 0, I get x equals 0. What's my horizontal asymptote? That's the shortcut method. I have 0x over 1x, which is 0, so y equals 0. So I have y equals 0, and I have x equals 0, like that. All right, and then maybe I need to do a little t-table to find a couple points. What if I plug in 1? I get 20. So 1 comma 20, way up there. What if I plug in 2? I get 10. Oops, 2 comma 10. And if I plug in 4, I get 5. And 5, I get 4. And 10, I get 2, right? Do you see how it's kind of curving? So it's doing this. I always miss my points. Okay. And then negatives work as well. I can plug in -4, I get -5. -5, I get -4, and so on. So -4, -5, -5, -4. So it curves like that as well. It's just like that last section. This is why this is in chapter 9. It's much easier than 9.3 though, right? Not so bad. All right, so, you know, I always talk about like when I'm tutoring and like people, like teachers teach the wrong thing. It drives me crazy. I'm sure I've taught the wrong thing occasionally, but there's some teachers that just teach the wrong thing every single year. And when I student taught, I just taught down in Evansville. And I had 2 super bright teachers. One was awesome. One was not so good. The awesome one, I loved her. She played a lot of games. We had a lot of fun in those classes. But she did teach a couple things wrong, and this is one of them. Because she was like, oh, well, one value goes up, the other one goes down. All it is just a line. And she would take those 2 points that she found, and she would just sketch in a line right here. I'm like, but it's not a line. It's not even close to the equation of a line because we have an x on the denominator. Like, it has to be a hyperbola. And so I tried to explain that to her, and she still didn't get it. And so I'm sure that she's still teaching her students that it's a line. It's not. It's a hyperbola. You guys see? You all understand it, right? Okay, so you will not go out there and teach the wrong thing. And when you're sitting around with your college roommates, you're going to be like, oh, yeah, y equals k over x, inverse variation, totally. Yeah, that's a hyperbola. You spread the knowledge, right? Yeah, you're like, whatever. All right, so joint variation. So the last, or there's 2 more. So this one's joint variation. When we say y varies jointly as x and z. So I would write y varies, I should have written this down, y varies jointly as x and z. If you hear something like that, then it's written as y equals k times x times z. Y equals k x z. Everything's on the same level. Nothing is an inverse relation. Okay, so it says the cost C of printing a magazine is jointly proportional to the number of pages P and the number of magazines M. So we just printed the ampersand magazine, right? Yes, Emily was part of that. And when we printed it, it cost a lot of money. It cost like $400 to print those little tiny books. Okay, and the reason it costs so much is because the number of pages in the book and the number that we printed, right? That's going to give you the total cost. Okay, so if we do this one, let's say there's a company, I don't know, some famous magazine, and they're printing 4,000 copies of a 150-page magazine. It's costing them $62,000. That's a lot of money for 150 pages and 4,000 magazines. We need to figure out what K is, what the particular constant is in this case. So if I multiply 150 times 4,000, I get 600,000. So when I divide it out, I get K is equal to 0.103 repeating. Or you could get it as a fraction if you want to. So I did 62,000 divided by 600,000. All right, so that means my new equation, if I was going to rewrite it, it's going to be 0.103 repeating times P times m. So the next question says, well, what if we decide we don't want to print as many pages? And I'm sure you guys had to decide this when you printed the interesting magazine. You probably had to condense things, put a lot of things on the same page, and so on. Okay, so what if we only have a 90-page magazine, but we print more? We print 5,000 copies. So we still use that same constant. Maybe I should write that. So it's going to be C equals 0.103 repeating times P times M. So C equals 0.103 repeating times 90 times 5,000. And I keep that 0.103 repeating in my calculator, so I do my answer. Times 90 times 5,000. And when I do that, I get a total of 46,500. Okay, much cheaper than the 62,000. Okay, so you can save money by printing less pages. Okay, so think about it in real life. What would the K represent in real life? It's the cost for what?
For each book.
For not each book, close. Each page, right? Because you're multiplying with the number of pages and the number of magazines. So it's the cost to print each page, so a little bit more than 10 cents per page. Okay, and then you could also have different combinations of proportionality. So this happens all the time in, science classes, math classes, and so on. All those formulas that we have involve direct and inverse variations. Okay, so it could be written kind of strangely. So there can be lots of combinations. You could have something as directly to the square root, but inversely to the square of something, So for instance, if we say y varies directly as x and inversely as z, we say y equals k times x, right, varies directly as x, but also inversely as z. So we do it all in one equation, so all over z. Okay, a lot of times I put this on the test and people write y equals k times x, and then they do a second equation. And they're like, well, y equals k over z as well. But then they can't find what k is. Notice how we're just putting it all in one equation. That's the whole point. So this one is about, a physics type thing. The resistance R of a wire varies directly, so varies directly as its length, but also inversely as the square of its diameter d. So all over the square of the diameter, d squared. That's how you would write that equation. Does that make sense? Okay, so that's 9.4. Pretty easy.